In this section, we will talk about the isotope and how to calculate average atomic mass. In the last section, I alluded to what an isotope was. It's an atom of the same element with a different number of neutrons, thus it has a different mass number. Most elements contain a mixture of at least 2 or more isotopes. Each one has its own abundance and its own particular mass. Each one will have the same number of protons. Lastly, I just want to mention that some of these isotopes might be radioactive. A radioactive isotope is one that is unstable and will go through the process of radioactive decay to become stable. We'll talk about that in section 4.2. If we take a look at the two nuclear symbols or hyphen notations that are on this page, you will notice that it is the same element. However, the mass numbers are different. You can see that in the hyphen notation form and also in the nuclear symbol form. Sometimes nuclear symbols do not put the atomic number because they know you can easily consult the periodic table to determine that number. Notice that you have a carbon 12 and a carbon 13. If I was to do the proton, electron, and neutron number for this, we would have 6 protons, 7 neutrons, and 6 electrons, whereas over here we would have 6 protons, we would have 6 electrons, and we would have 6 neutrons. Notice that the number of neutrons are different, but the number of protons stays the same. That is the definition of an isotope. If we take a look at another example, you can see that we've got 3 isotopes of lithium. Notice that they all have the same atomic number, but they have different mass numbers. So they will all have 3 protons, but they will have a different number of neutrons. In the first example, you would have 3 neutrons. In the second, you would have 4. And in the third, you would have 5. The number of electrons would also stay the same at 3 for each one, because we do not see a charge in the nuclear symbol. In the last section, we talked about what a mass number was. It was the sum of the protons and the neutrons. It was always a whole number. It was for only one specific type of atom. In this case, we're going to say isotope. And it is not found on the periodic table. That is different than the average atomic mass, which is the average of all the actual masses of the isotopes that exist. It is not a whole number. It will be a decimal number. It will be found on the periodic table. And we're going to calculate it using a weighted average calculation. Let's do a quick practice problem. So in Miss Soto's chemistry class, her semester grade is calculated by looking at your major grades, which are 60% of your grade, minor grades, which are 30%, that would be your formal and your informal, and a semester exam, which is 10% of your grade. So let's say you're the student and you have an 80% for major grades, 60% for minor, and a 65 as an exam. If we were to take the 60%, which would really be 0.60 times 80, we would get 48. 30%, which would really be 0.30 times 60 to get 18, and 0.10, which is the 10%, times 65 to get 6.5. If we added all those up, you would get 72.5. That is an example of a weighted average. A normal average would be just taking those 3 percentages, adding them up, and dividing by the amount that you added up, which in this case is 3. And you can see that there is a significant difference here. So the way that I calculate your grades is actually how an isotope's average atomic mass is calculated as well. You can see the equation for calculating average atomic mass down below. Basically what you're doing is you're taking the sum of each isotope's abundance times mass. The abundance of the isotope will be in decimal form, and we generally use the mass of that particular isotope. If that's not provided, then we'll use mass number, but most of the time it will be given to you. So let's do an example. We want to find the average atomic mass of chlorine. You are given chlorine 37's mass and percent abundance, so you can see that in the data table. And you can also see that chlorine 35 is the other isotope. You've given its mass, but not its percent abundance. Now we know that if we have two parts, they total up to a whole. A whole in percentage would be 100. And if I subtract 24.22 from 100, I end up getting 75.78% abundant. So that is going to be the mass percent of isotope 1, as seen in the data chart. I'm going to change those to decimal form, and then I'm just going to use the equation. The sum of the product of the decimal form of the percent times the mass of each isotope. And when you do that, we don't want to round until the end. You'll end up getting 35.45 AMUs, and that's exactly what's on the periodic table for chlorine. We generally take our sig figs to at least the hundredths place, maybe even the thousandths place for average atomic mass. Alright, in this example, element X has two naturally occurring isotopes. The first isotope has a mass of 10.012 AMUs, and it's 19.91% abundance. You can see that in the first row of our data chart. And the second isotope has a mass of 11.009 AMUs, and it's 80.09% abundance. Notice that these do add up to 100%. Alright, so now that we have that information, we're going to plug it into the equation. The sum of the decimal form of the percent abundance times the mass of each isotope. So this is isotope 1, and we're going to do it again for isotope 2. When we multiply 0.1991 times 10.012, we end up getting 1.99338892. When we do the product of 0.8009 times 11.009, we end up getting 8.8072. We're going to add those numbers together and round to 2 to 3 digits to the right of the decimal point, and we end up getting 10.81. The unit is AMUs. And if you look to the periodic table and find the element that has that mass, you'll notice that it is boron. This is your self-check. Go ahead and try to get the answer to this problem. Calculate the average atomic mass of copper if it has two isotopes, and then come back and see how well you did. Alright, hopefully you noticed that there were two isotopes. One was 69.11% abundant, and you were given its mass, as seen in the first row of the data table. And the rest has a mass of 64.93. Basically what we did here was we subtracted 69.11 from 100 to get 30.89, and then we went ahead and filled it into the equation. The sum of, remember this is isotope 1, we're going to get the product of that value, and we're going to add it to the product of the value for isotope 2. Remember, we don't want to round until the end, and we end up getting to the hundredth place, 63.55 AMUs. You can do a quick check, and you'll notice that copper on the periodic table has the exact same average atomic mass. Alright, this concludes our second portion of section 4.1. We will do more of these in class, and we'll kick up the difficulty level. See you then.